let's get things started. So again, right? See, it is curious, right? So I think now from you can see the idea of learning a distribution in the high dimensional space is not unique for 不是现在做 CS 的，不是我们 it's not started with some computer generative model, okay, generative AI, okay. No, we're too obnoxious to think we're the first, right? The people are doing the generative AI come up with idea to learn some distribution in high dimensional space, right? Physicists that started that interested in high dimensional, especially statistical physics, right? 统计物理早就这样想学这些材料，对不对？对物理、分子、运动啊，建立这些物理模型，对不对？热力学的定理大家找这个，还别说量子物理里面很多的这种原子、分子层面的、材料层面的这些高维的它的结构解释。OK, discover the geometry, statistical behavior of those large number of atoms, large number of materials. Okay, that's the hundreds of years of history. They're interested in different type of models. In fact, if you look at the early days to investigate the image distributions, right, all things are inspired by that branch of, in the first chapter 1 I mentioned, right, even David Mumford, right, started to study the geometry, try to model natural images using random fields, for example. Right? How to learn those distributions using MCMC, Markov or Monte Carlo. They're all actually started with physicists. They're interested in understanding the high dimensional geometry of statistics of distributions. Okay, the behavior of those. But we didn't start it. We have a lot to learn, to know. And almost all the ideas, right? If you think about all the ideas, we actually implement in the past 10 years, all the generally actually from physicists. Denoising, right? 而且同样重要的问题，你发现没有？同样重要的 idea, the most important idea gets reinvented, right? Early this last century, when people were interested in thermodynamics, high dimensional statistics. And then 1940s, Feller, those guys did how to learn using denoising to learn distribution. Then gets reinvented by 60s, right? Statistician try to interest in denoising. They rename it as the Bayesian, empirical Bayesian denoising, right? Then in the 1990s, gets reinvented again in signal processing. People try to do denoising. In early 2000, again, by machine learning people, right, called the score function, right? Then reinvented again, right? Reintroduced again, 2015, right? By physicist Ganguly. Of course, nobody cared. Because why? Everybody else is busy with GAN, with other things. They think it's popular. They think it's the right thing, right? With absolutely no scientific justification, theoretic justification. But everybody, this is it. Then 2000, again. Right? So the right idea, see, this is the thing, what academia is about, right? The right idea, the 正确做事的方法是不变的。没有那么这个奇异技巧 ，OK？ 没有什么这些什么 shortcut，OK？ 往往正确去做一件事情的方法就一种，大道至简就一种正确。不要认为自己临时发现，这个好像可以这么来，对吧？这么 heuristic 吧，这么东西你就可以。No, you never, you cannot. Okay, always back to the right direction, no matter how much detours you do. So hence. You wanted to know what's really the idea, the principle behind it. Right? And so this is something, right? This is approaching to learn such a distribution, high dimensions. But now we know the idea of denoising, compression. We can approach, at least give us a way to approach those data, right? In a very high dimensional spaces, the place where the data is. But how do we actually end up with there? Where do we end up with? We end up with the data itself, or we end up with the structure support the data? 到底这是怎么回事 ？Okay, 怎么不动了 So today I'll just do a little bit. In fact, this is a problem, honestly, that intrigued me when I was just, very early on to study data, the geometry or statistics of high dimensional data, such as images, a long time ago, right? I'll give you a little bit, our understanding. There's a second part of chapter 4. It's about how do we understand the data finite samples coming from the low dimensional structure? Right? Which one is the right interpretation? 这些点他们自己，还是这条线 I gave the example, right? Remember in the chapter 3, right? The 8 points example. 还记得吗 The 8 points, 8个点，均匀分布在一条线上 ，uniformly or cluster 4个点很近，另外2个点2个点，对不对？那你去想，你们有没有回家睡觉前想一想这个事情 ？How should we interpret the data? Why? What's wrong? Just call them 8 points. Why you should call them a line? 对不对？你什么时候它应该是在这条线上？要增加一个维度。那为什么第2个分布，对吧？不均匀的跟均匀的又不一样呢？都是8个点，每个点出现了1%次。What's the difference? Why those 4 should be clustered? What do you gain from it? What's wrong? 这8个点都是在一个平面上。Why you do not prefer? Why you prefer one explanation over another? Why? What's the criteria? What do you gain from preferring one interpretation versus another one? 对，如果你都没有去想过这种问题，那就很麻烦了啊。那你可能这辈子就稀里糊涂了，对吧？别人告诉你是什么就什么了，对不对？要去找到它的原因是什么 ？Can you attempt to give an explanation? A convincing explanation. Other people can agree with you. Right. So we know the goal, right? From the very beginning. I mean, of course, after we know our data is kind of like this, right? The data lies on all the very low dimensional structure in high dimensional space, and we try to find where they are, and also maybe even transform them to something structured, right? To find them to do that. In fact, now if you go back to early 2012, right? So when the deep network first saw its success, it's about the classification, right? To have the data, this apples, orange, birds, right? Data. Then we try to map to 1000, 01000. So if you know all this classical Alex Let, right? Let is doing, right? We build a network, try to fit this mapping the data into such a label, class label, right? Now, if you think about this class label, they're exactly code book, 对不对？它实际上是一个非常简约的，每一类我就给一个 label， 对不对？这是最简单的代码。But this code is very lossy. All apple becomes 1000, 对不对？我不再区分不同的 apple 了，长得不大的、屌的、红的、青的我就不管了，明白吗 ？Everything gets just converged to one, just one point, 对不对？ So this is a very simple code representing the class label, 对吧？所以你可以从数学角度上，这就是 assign a very simple code, very lossy, almost extremely lossy code. Only preserve the minimal information about the different classes. That's it. Right? Hence, even the object function to train neural network is precisely minimize the tail divergence. This is actually called the cross entropy, right? This is exactly, see, my predicted label has to agree with the given label. Okay, this is actually the cross entropy is exactly the tail divergence. Actually, to check, right, to minimize them. It's actually a correlation of the predicted label and the actual label, right? The predicted label and the actual label, right? This actually is precisely minimizing the coding length, right? Cross entropy between the data. So if you find the right label, right? The prediction of the label and the coding length is the smallest. Right? So this is actually has a very clear. Of course, people find this is also again has some very weird. This is also another best paper award, by the way. Right? Again, it's purely experimental, right? From Berkeley. Actually, 17. Deep networks, they actually try something very interesting. Right? If you choose a very powerful network, F is very powerful, right? You can randomly, every pair, every image has a label, right? You can randomly change that label. Apple to tiger, tiger to monkey. Okay. Just rechange X and Y the pair. Change the label arbitrarily. Then the network is able to fit that data set perfectly. The training error goes to 0. Not only that, you can randomly shuffle the pixel in the image. Okay? You still can get the training data to shuffle pixel randomly, add an arbitrary Gaussian. In fact, you can just, the image is just random Gaussian, you give a label. You can still fit it, right? So there's all kinds of interesting things. So what do I actually do this? Does the network just memorize the data? Right? Learn something useful from the data distribution? See, this kind of data has no structure whatsoever, but the network is going to fit them anyway. So you can memorize. Basically, network can memorize. Right? This is just evidence. If you give a very powerful network, it can memorize whatever relationship you give to them. So hence, when it become useful then? When does it generalize? Right? Or不是 fit arbitrary noise, arbitrary data points. Right? Of course, people come up with all kinds of interesting theory to try to explain this. One of the dominant, very popular theories so far before was, let's try to, the network must learn some feature, right? Although I don't know what the heck it is, but say let's learn some feature, somehow can keep all the information about the label, the class label, but irrelevant to, just filter out all the information in X that is irrelevant to predicting Y, right? They call it information bottleneck hypothesis, right? They try to maximize this kind of feature learning, deep learning, trying to achieve the task, right? But this is the problematic. Why? Because this is always related to a specific Y, a specific task, right? It doesn't tell you what you learned about the distribution of X. Right? What if I change the Y? Right? So the feature, 所以这个是一个大问题。所以这就是一个 generalizability 和不 generalizability 的问题 ，right？ 所以你看很多网络，我们现在如果把一个网络去 fit， 只是去 fit 一个 x 到 y 的 mapping 的话，这就很麻烦，这个东西很难 generalize， 对不对？比如我一个图像，我要去 predict 它的类别，我训练一个网络。如果我只关心颜色呢，训练另一个网络，对吧？我又只关心，比如说这个物体的大小呢，我还训练另一个网络。所以这就是个问题，对吧？所以你看现在包括这些什么很多的这个网络，对吧？都是这样，机器人也是这样，对不对？我完成这个任务，抓东西训练一个，对不对？转东西训练一个，转笔训练一个，开瓶盖训练一个，所以才会有1000篇文章。OK， 那么每个人就玩一组数据，一个 mapping，one condition，one set of parent， 你们可以继续写啊，同志们，鼓励你们继续写。但不要奢望你在历史上会留下任何名字 ，OK？Because nothing will generalize， 明白吗？你可以不同的 label， 所以大家都是所以你看这个 AI 挣钱的是什么 ？label 数据的，对不对？还有卖芯片的，对吧？就是你就是不同的 XY， 我就 fit 一个网络嘛，对吧？那就是 achieve that one task. This is a problem. Now, what's the right way of doing things? We have a memory, 对不对？ We memorize the world. we've been to this place, been to different place, we memorize, but we memorize not for a specific task， 对不对？比如说 I've been to Rome， 去罗马，对吧？我记住了大概的地图，但有可能我是从一个地方到另外一个地方，有可能是去找饭吃，对吧？有可能就是去，对吧？买张车票，可以做不同的事，有可能就是去见一个熟人 ，right？ So our memory serves different purpose， 明白吗？不是一个 particular pair of task。所以 what's actually important is learn what this guy is. Right? Because in the future, the potential task, the y associated with a particular task, maybe is a different function of x. 明白吗？ So the memory of x, learn the distribution of x is important. That's why actually later on, this is a sort of discriminating method. Later on, people move to try to learn x, right? To add sample x. That's why the shift from fitting this model, fitting this input output to something more towards to learn what x is, to learn representation of x, right? Hence, the study is shifting from discriminative to more generative method, right? Try to get a hold of the distribution of x. So hence, I can support more tasks. Right? Depending on the task, the y may be a different function of x. I'll be able to do Bayesian inference. We'll get to that later. So, but there's a lot of issue. Before we do that, right? There's actually a lot of issue with all these things, right? We talked about this a little bit before, right? For example, when you talk about low dimension, so there's a lot of issue. The distribution, we know that the data in the high dimensional space, but if the structure is low dimensional, there's a lot of issues, right? This is actually about 20 years ago. This baffles me a lot, right? As a student, right? Because if you learn a little bit statistical geometry, right, you start to realize that first of all, when you're dealing with the distribution in the high dimensional space, there's a curse of dimensionality. If you're talking about generic distribution, if you want to learn it, remember I just give that example, right? 如果你认为你的数据就是高维空间中的一个 generic 的 distribution， 就是很一般的分布，哪儿都有的话，比较肥的那种啊，就是胖的那种 distribution， 对吧？或者一个 generic 高式的话，那你就完蛋了，对不对？因为要学那样的 distribution， 你要的 sample 就是 grows exponentially in the dimension。你哪个地方都要看到一点，对不对？你每个地方的 density 都要 estimate 一下吧？那就对不起。You have to see everything. The number of sample you need goes to 1 over epsilon to the n, to the d dimension. Okay? You suffer from curse of dimension. 所以去 learn 一个 generic distribution in high dimension is impossible. 甚至去学一个高斯分布在高维空间都是不可能的。OK？ 都是 complexity 都是足够高的，所以你就不要想了，对不对？好 ，Second, now what's your option? Then the distribution cannot be generic， 对不对？就不能是胖的，对不对？不能是 fat 的 distribution， 那一定是瘦的，对不对？一定是有低维结构的，对不对？这有 hope， 对不对？前面的那个前面那堂课也给大家一些 evidence， 包括像图像，对吧？都是这样的分布。自然的有结构的数据基本上都是在低维的高维空间中的低维结构，跟你的 ambient space 无关。OK， it's actually the intrinsic degree of dimension is actually irrelevant to the ambient space where you embedded them, right? It's always nine-dimensional. You can embed it in any dimension, right? Intrinsic dimension is much matter. Fine. If that's the case, now you have something else to worry about, right? Then you start talking about what's the distance between the distribution, or the KL divergence, even entropy, becomes not defined, right? Differential entropy goes to negative infinity. Maximum likelihood blows up to infinite. KL divergence is not defined. 因为两个 distribution, if two distribution, their support is not overlapped, the KL divergence is not defined. Okay? Then what the heck are you talking about? 你去想一想，你们有没有问过这个问题？对吧？所以我很 baffled 的 ，right？ 所有的 Lips 文章啊，一开始都是we are computing KL divergence， 对吧？we are computing maximum likelihood, right? In VAE, we are approximating it, right? Posterior, right? Jesus, they're not even defined. What the heck are you talking about? Right? 所以大家你们同学们有没有知道这些东西，对不对？这就是 technical 的对吧 ？rigor。这些看似的数学概念，它是有条件的，对不对？ 这些量的定义 ，this definition has conditions，对吧？几万篇文章全是这么写，对吧？然后最后发现这个计算不了，right？哦，this is not hard to compute 啊，认为 that's approximate，对吧？Let's approximate this, approximate that. After a couple of persuasion, you have no idea what they're doing. OK， 是不是？全是一锅浆糊在那儿，对吧？一个的几十万篇文章全在那儿搅浆糊，对不对？所以它没法 progress。So this is actually very, very. By the way, also that you only have finite samples, right? From such a high dimensional space. Then how do you reconcile from finite samples to such a distribution? How do we bridge those? Right? It's not very clear. Those are the very fundamental questions, right? How do we resolve this? I mean, I can tell you about 20 years ago when I was a graduate student, those actually, confused the hell out of me, right? I studied statistics at advanced statistics courses, but then I started to apply some of the, principles to real data, such as images, to do image segmentation, classification, and start to realize them, and doesn't make any sense technically. Yeah. So then we're dealing with data that really have very low dimensional structures, right? With some noise, they truly have very low dimensional structure. Start with simple ones, planes, right? Maybe with some noise, with some outliers, right? So can we actually, how do we identify the structure behind them? Right. But this is another lesson, right? When I was a student, graduate student, right? When we do clustering, 如果你们去读 Hinton 80年代在干什么 right? To system ID, to do data clustering, classification, right? So for example, this is a classical problem, classification. Before deep network, okay? I have data from mixture of some distribution, right? P1, P2, Pk, 对吧? I have like K mixture. So we write down the distribution like that. Maybe each one is a Gaussian or degenerate Gaussian, whatever, subspace, right? Some with mixed with proportion pi, so on, right? So this is like a classical, if you take any statistics course, probability course, right? 对吧？不管是硕士、博士，对吧？上课都是这么教你的啊。This is actually distribution, right? Mixture distribution. We write it down this, and this is a parametric family, maybe Gaussian, maybe Laplacian, maybe some, sub-Gaussian, some, exponential family. Then what do? We have samples, right? From those samples, K samples, right? Then what do? We maximum the likelihood, 对不对? Find the theta such as the maximize the likelihood of this function. We do this. This is what. Then how to solve this problem? Anyone know? The classical algorithm to solve this kind of mixture problem. Hinton 也写过这个文章的，80年代，后来全彻底放弃了，对吧？ What is the classical algorithm to solve this mixture of Gaussian, a mixture of model? 没有知道吗，同学们？你学过 pattern recognition 吗？ Anyone learned pattern recognition? 没有。Seriously, okay, you guys got to learn a course on machine learning or pattern recognition. 所以你们还没学任何有用的东西啊，这个无用的东西都没有学，还别说有用的东西啊，这是没什么用的东西，但是这个挺重要的东西。OK, the algorithm is called EM, expectation maximization. Okay, so you're alternating between estimating pi and the theta. There are two parameters, right? The mixture proportion pi and also the parameter theta. You alternate minimizing them, right? There's a classical algorithm called expectation maximization, right? So maximizing against theta, expect the membership, okay? How many points belongs to each cluster, right? This is a classical EM algorithm. But of course, nobody uses it. And they teach at every probability or pattern recognition courses, 对吧？所以这是一个很奇怪的现象，对不对？我们的课程教我们完全不用的东西， 啊，世界上没有人这么做 clustering 的，OK？除了 assign homework to students，right？For practical data, nobody uses this 啊，所以这是很奇怪的一个东西。我们教一些学生，我们自己都不用啊，所以后来大家开始玩 deep networks，对吧？这是因为你统计教的东西都没用嘛，对不对？所以这是一个很讨厌的一件事情啊。Of course, for if you really have a generic Gaussian, this actually works okay with 当维度很低啊，模型还比较 generic 的时候，比如一些二维、三维的高斯啊 ，two, three-dimensional Gaussian, this is a mixture of three or four components. It actually works okay. Okay, but that's about it. It's very much on the simulation level. For real data, this doesn't work. Okay, especially why? Because real data, unless those distribution become degenerate, the maximum likelihood is not defined. It blows. Okay, so useless, right? But it's actually beautiful theory you can learn, right? That's why we teach students, although it's useless. Right? So that's why actually got me to think, right? This is about a few years ago, right? About 20 years ago, right? When we look at this problem, it's really that why the heck everybody do EM, but nobody use it, right? In practice, everybody do all kinds of hacky thing, right? Clustering this, clustering that, normalized cut, 或者什么的 KSVD, everybody doing different thing, right? Nobody using EM algorithm, right? Of course, later on people do neural networks. Okay, that's a different story. But that was 20 years ago, right? So we start to realize what the heck, why we want to classify? Why you want to clustering? 大家有没有问过自己这个问题？所以你看我们的课程有一个 recurrent theme， 对不对？就什么是 first principle？ 我想通过这个课程教大家啊，你的目的到底要干嘛？你为什么要做这个事情？大家有没有问过为什么？哦，人家说 classify 我可以写文章，对不对？可以发文章，我就去 classify。这个数据上 classify 是可以写文章，对吧 ？percentage 高一个点就可以发个文章。你 Why in the world do you want to do it? What do you gain from it? Why do you want to classify? What's wrong with not classify? 问一问你自己，对不对？我们不 classify 和 classify 到底的区别在哪里 ？If we have data, for example, like this， 哎，这两坨的数据，对不对 ？If I don't classify, how do you measure? How do you measure what you gain from classify correctly, not classify correctly? What if I don't classify? Or what if I classify wrong? 对不对？哦，因为马老师或者人家每个人都用这个，对不对？这个 cross entropy 对了，我就得分了，对不对？我的 percentage 用这个训练完，我是比别人高1个 percent， 我这个 Why in the world you do this？ 这个东西对吗？如果没有 label 呢？这还是有 label，没有 label 呢，我怎么办呢？神经网络可以 fit 任何 label。等乱上一个 label， 对不对？随便让那个神经网络一 fit 不也挺好吗 ？Fit data perfectly. What do you gain from this? Right? So this actually have a point about we call it what do you gain from it? 你能不能去 measure 一些东西？非常简单。What is the basic measure? You can tell the difference. Right? So one idea is that you have to reduce this to something tremendously basic to make sense. OK? 就还原到 first principle。你到底怎么去区分数据分开和不分开？用什么去区分？其中一个量 ，one measure you can do is volume. OK? If your data like this, right? If I don't cluster， 我不把它区分开，那么 if I wanted to 把这个数据装在一个空间里面，把它装起来，拿一个口袋把它装起来。Specify the region where the data is, and also where each of the point relative to this region. I need a circle like this, right? I need a space to contain all the data. That's the volume I need to contain all the data. And then specify each data point where in that volume, where that point is. Right? How do I specify where this point is? Easy， 对吧？我也告诉你们，对不对？这么大的 volume， 怎么把这个 location 记下来？塞满豆腐，对不对 ？Pack spheres. Then remember every point which sphere it fills in， 对不对 ？Depend on the accuracy how we find one， 对吧 ？Measure the volume and code the volume, partition the volume. Very simple, very basic. Nothing more basic than this， 对不对？好。Now, if I do that, I need this big space, right? Then every point I have to specify in the space where its location is. Well, that's the price I need to pay. Hence, roughly, to hold all the data, the volume I need is this ellipsoid. Right? Now, if I'm lucky, the God tells me, oh, this is together. Those blue points are together. Those green points are together. Then I can have two bags. Each one is much smaller to hold the blue ones and the green ones. Then the volume is much smaller. The total volume add together is much smaller, 对吧? So in terms of bits, number of balls fill in the blue space or the green space is much smaller. 所以每个点相当于这个小 circle 它要的 code book 就少多了，对不对？如果你把这个 if I fill this space with epsilon ball, the number of balls is much smaller. Hence this 这个点要去 specify 那个 ball 的数值，对不对？ The digits 要少多了，对不对 ？Versus fill the whole thing with spheres. You need a much longer digits specify which ball it is, 对不对 ？On average. 明白吗？对吧 ？Bits 只是一个 unit，OK？、Okay? 你也可以用 centimeter， 对吧？你也可以用 millimeter， 啊 ，depends on the precision。Hence, at least from a volume, basically, if you partition the data properly, you gain from the volume， 对不对 ？So hence, if you can measure the data, the volume, that becomes a measure of gain， 对不对？而且我们也知道，对吧？我前面也讲到 ，this is exactly what entropy is measuring， 对不对 ？Entropy 就是在数据的 entropy 就是在 measure 一个数据分布的 volume。It's a generalized notion of volume. Okay, you pack the space with epsilon ball and count how many balls shows up in what frequency. Okay, that's it. Take an average. That's actually the coding limits. That's how many bits you pay in order to memorize data drawn from such a distribution. 明白吗？ So the clustering, the gain is exactly volume. If I can partition the data back properly, I gain the number of bits, I gain the volume. I use less volume to remember, to store the data. Right. Now we're talking. Now this can be a first principle, right? I can use this to measure if my data is properly classified or properly clustered. I can use this ultimate, rigorous, objective measure. 这个 measure 可不是以人的意思为转移，对不对？这是一个客观的量，这个 entropy 一样，不是说你选这个 loss function， 你来选那个 metric， 对不对？你选这个 feature， 对不对？现在这个为什么 machine learning 一锅粥，对吧？你选这个 feature， 我选这个，大家都是 hidden， 都是 latent， 对不对？你的 loss function 不一样，而且你选这个 weight， 他选那个 weight， 而我比你好1%， 你比他好1%， 对吧？就瞎搅和在那儿，对不对？大家都在那儿弄不同的这个 objective measure， 这个不管啊。这个是一个客观的量啊，对吧？不以人的意志为转移的，唯一你能选的就是你有什么样的精度 ，What's the precision to measure the volume? That's it, right? Up to centimeter, up to millimeter, up to对吧 ？Micrometer, it's up to you, 对吧 ？But once that's settled, let's compare. Hence, how do I measure the volume data, right? Especially if I have data draw from some subspaces or some Gaussian distribution. Okay. Right. So you have data draw from Gaussian or from some subspaces, low dimensional subspace spanned by, let's say, U. How do I measure the volume? How many bits I pay? How do I properly quantify the space? Count how many balls to fill that support of the distribution. Wow. 你看 假设我的数据在这个区域，对不对？有高斯分布，大概集中在这里。那我怎么做呢？我得把这个区域用 y 包把它 fill up，对不对？算一算嘛，然后哎，这是1、2、3、4、5，把它标好，这是512。所以当任何一个点出现的时候 ，x shows up sample. I say, oh, this is 128 ball. Hence, this sample I recorded as 128. That's the number of digits, right? This is a code book. I remember this sample. Of course, this sample could be anywhere in this sphere, but it's okay. That's a precision. The sample gets memorized up to the epsilon ball. Right? That's my choice. If you want a more precise, make the ball smaller. Hence, the numbers tells me I need the 128, convert that to binary. It's just the units, 对不对？How many binary bits is 128? That's how many bits I need to record x. Okay? Then another position, then take an average. That's we call the coding rate or coding length of the data x. 说白了就是 x span 需要多少个 binary bits to record 它，就是 x span 的 volume。Right. So the more refined I know the location of the data, the codebook can be more optimized. That's why the codebook needs to be learned. Right. Here, let's say we already given it's a Gaussian, right? We already know what the distribution is. Right. Remember that distribution also needs to be learned from sample. That's a different story. Okay, we'll learn. We do that, right? That's why dictionary learning, we're learning those dictionary. But suppose the dictionary is already given to us. We know this is already Gaussian, already subspace. Then what is the number of bits for data randomly draw from such a distribution? What is the coding length? If the coding book is already given to you, it's a Gaussian subspace. Turns out this is a formula, right? This is 这个 Shannon 他们可能就是七八十年前就已经 work out, right? Turns out if you give an arbitrary distribution, right? The coding length is very hard to find the optimal code book. Also to measure the coding length, it's very hard. Actually, it's NP hard in general. But fortunately, for Gaussian or subspace, it's easy. There's almost closed form. So this is, you have data in the D dimension, the ambient space. Those are the vector in capital in RD, okay? It's a vector in RD. And the dimension of the data, you have n points. The quantization there is epsilon, right? The radius of the ball is epsilon. Okay, that's a quantization error. Right? You fill the space with that epsilon ball, and this actually makes a lot of sense, right? The formula look a little bit complicated, right? This is essentially XX transpose. What is this? This is a covariance matrix. 对不对? Use XX transpose divided by M. That's exactly covariance matrix. Looks like the shape. And the determinant of the covariance, that's the volume. 还记得吗？对不对？ Determinant of a matrix, 这个 matrix span the volume. OK， 这个多边体，对吧 ？Determinant of multiple vectors， 实际上是这个volume 在高维空间中的一个 generalization, right? Determinant is actually the volume. 取个 log 是什么意思？这个 volume 用多少 digits？log 2 digits 来 convert to digits, binary numbers. OK， 把 the volume 用 metric 变成 digits， 然后前面有些系数这么多个点加的 overhead. OK, those are the overhead. How many points? So if I care about the average per sample, I divide by m, right? When m is large, this goes away. 对不对 ？If m divided by m per sample, you have to divide by m. This 消掉，剩下就是1/2啊。这个 d 就收 d is fixed. M goes to infinity. There's 1/2. So coding rate is always 1/2 log determinant of its covariance. OK， 明白吗？所以这是 M 个点的总的重量质量的这个体积，对不对？但是每个点的平均的体积是 1/2 除以 M， 明白吗？ That's coding rate， 编码率这是 coding length， 是 total 整个 data set 的 total coding length， 整个 M 个点的。So this is actually a very interesting formula, right? We actually derived this about 20 years ago, right? 2029, we actually derived this. And it turns out that this is not only, this formula is quite interesting. Not only in this formula is measured, your data have this Gaussian distribution, it's the same formula. Also, you can prove when your data is purely algebraic. If your data is sampled from a low dimensional subspace, this is exactly the same formula. That's very interesting 啊，所以很有趣啊。你看这个 formula， 它又有几何的纯统计，又有纯几何的解释。不管你的数据结构是代数的还是统计的概率的结构，它的 formula 是一样，它的 volume 是一样啊。所以我再给你们讲一下啊，从高维几何里面、高维统计里面提到一个 ，in high dimensional space, geometry is probability, probability is geometry 啊，尤其是 in high dimensional space, geometry Gaussian distribution is subspace, subspace is Gaussian，OK， 它们基本上是 behave 是一模一样的啊，没有什么区别。所以在高维空间中，甚至一大 concentrate, they very become very similar to each other. Right. Okay. So now once you can measure, at least for Gaussian, piecewise subspaces, now you can measure. You have a very clear measure, right? If I give you data, I partition them, then I can tell if my partition is worth it or not. 我值不值得？我要不要这种 partition? Right? Now you can see if I can code the data as a whole, or I do the segmentation, right? C stands for segmentation classification. If I classify them to 1 or 2, of course, there's some overhead. This is a Huffman code because I have to pay some extra price, right? For every point, I have to tell me, I have to record X, this point belongs to X1 or X2. 但这个很容易，这就是 Huffman code， 对不对？你要配一些 extra bits， 每个点你得告诉我它属于某一类啊，这是 Huffman code. This is also optimal code, the membership of each point, right? Besides this, each one has a volume, right? This one is the volume of this one. This is the volume of the second one. And this one is just the how do we split the data, record the class label, right? So actually, see, this is a completely objective, 对吧？所以这里面就是右边的这个东西，这样完全就是 bits， 就在数数 bin counting， 对不对？就 specify， 所以 if 的右边是比左边短小 ，if the right hand side is lower than the left hand side， then I go ahead. I prefer this than that， 对吧 ？If it's higher than that, if I split wrong， 对吧？我把这个分错了 ，then I don't do it. Right? If the data does not allow, 因为 partition there's always overhead， 对不对？ You have to memorize which point goes to which class. You have to pay some price for it. Right. So if data doesn't have cluster structure, if you do the partition, you don't gain anything, you lose. Okay? But if it indeed has low dimensional structure, if you partition, you gain tremendously. So you can use this measure, this ultimate measure, the volume of the data, to justify why do you want to classify, or why do you want to cluster. Okay? This is ultimate measure. 这是你要做一件事情的目的，明白吗？你是这样去 justify， 而不是说别人说这样啊，这个数据你去分，对吧？分的比别人准，你就可以发文章，对不对？不是这个道理。Turns out there's something very interesting, right? If you have data has high density along some low dimensional sparse, turns out if you split data like this, this is also preferred solution than not splitting the data. 你看这个甚至像一个 continuum， 对吧？在一个平面上。但是如果有些数据 ，if a subset of the data has higher density concentrated on low dimensional subspace, like a line, separate those points away from the rest. The rest is still lying on the plane. But those one get it out. Again, this will be better than that. So you actually can sift out low dimensional structure in the context of. So you don't see this kind of phenomena in other kind of classifications, right? 你要这么去看的话，你看这个根本就看不出来什么结构，对不对？都在一个平面上啊。But turns out, if you use this criteria, if you do it right, you will actually find that this is the preferred solution than that. Okay? You actually gain by discover something low dimensional. Now, how do you partition? Here is the question, right? See, you're lucky, but why do you do this? Why do you do this one, right? What about this cut? About that cut, right? Or there are there are gazillions of possible cuts, right? You can split the data. Do I have to try all of them? Especially if I give you a data set, what if they're K cluster? K 很大 ，n points K cluster. So what's the possibility if you assign any point? That's n choose K, 对吧？ That's a huge number. If K is large, n is large, the possible combination, possible way to split data set into K class is huge. Is n choose K, 对不对？是组合数，对不对？ Then that's very expensive to check all possibilities, right? That's very dumb. Well, by the way, most of the big network is doing that anyway, right? They're doing search, right? So you can do that. If you have like 1,000 GPUs, you can probably do very clustered. But anyway, so how do we do this? Turns out that, one way we did it is a long time ago was something very simple. We don't cut. We merge. So first you make every point its own class. Then you merge two, you check pairwise. If you merge 2 points, you can save bits after. So if you're lucky, the 2 points lies on exactly on the line, straight line. Then they form a low dimensional structure. It actually can gain. If you only merge them, if the coding length is smaller, is negative, then you merge. Otherwise, you don't. So you check all possible pairs. If you can merge them after merging, you identify a low dimensional structure. You save bits, you do it. If you don't save bits, you don't merge. You leave them alone. Leave that pair alone, right? So this actually ends up with you reduce the algorithm into n choose 2. The complexity of which is quadratic. The complexity of the algorithm is quadratic of the size of the data. Right. So this is manageable, tractable. Although this may get stuck with local minima, 对不对? But that's fine. This is probably a greedy algorithm. So we tried this about 20 years ago. It actually works the best. So far, in my opinion, this is still the best clustering algorithm, especially when your data has a mixture of linear structure or Gaussian structure. Okay, you can find. We still cannot find anything to replace this. Right. This is still unsupervised learning algorithm, the most powerful one. So actually, see, you can have very high noise. This is one plane, 2 lines in the plane. You can see you have very high noise. It's still getting the line, 2 lines, and the plane identified clearly, correctly. And you can even add 50% of outliers. Still gets classified clearly. 更有趣的事儿，对吧？是这个。There's a clear phase transition. Right? Remember, this is about 350 points. Okay, they start merging, right? When epsilon is very, very small, epsilon is very, very small, then no points gets merged. 对吧？因为每个点都画地为牢，对吧？就是我跟我邻居的距离，比如说我们是5米，对不对？但我的 epsilon 就是0.2米， so you never connect with each other. You never merge with each other. But when the epsilon grows, at some point, so 这有点像什么呀？ Every atom is on its own, right? It's like steam. 明白吗？就像那个水蒸气一样 ，Every atom is completely unknown. Nobody connects with each other. But once you increase the epsilon, which is kind of reduce the temperature. At some point, 你看它 at some point 一下子变成所有的点连成一片 ，There's only one cluster. 一下变成像水一样，水蒸气变成了水，全连成一片了。There's only one cluster. 而且在很大的区域，对 ，epsilon can change from several magnitude, okay? From -7 to -4, cross 3个数量级的 epsilon，1000倍变化的 epsilon， 这个 solution 不变，就一个解，都是 water， 非常 stable。再降低温度 ，something interesting happened at this point， 一下变成3块，也是 very sharp transition。epsilon 变成了一点点，啪就从水变成了冰块，3块冰出来了。Nobody knows， 而且又是你看，又变成了 across 大概3个数量级的 y，y 可以变非常快，从0.1到100，solution 不变，都是同样的级。然后再往下降低温度，y 再大，大家全部变成1。当 y 到足够大是什么问题 ？When the y become huge, infinite, the whole universe is just one point, right? My tolerance y is huge. I only need one point. The center of the universe to record any phenomenon, right? Because y is huge. So 变成了绝对0度嘛，大家都不动了嘛，就一个结论。It's very simple, right? So this is a very interesting phenomena, right? You can run this algorithm. You can try. Extremely robust to noise, outliers, and so on, right? So far, there's no theory. Okay. 这是我跟 John Wright 大概20年前毕业前做的工作啊。It's very striking phenomena. This is phenomenon of emergence. OK， 所以什么 scaling law， 什么这个 emerging 那个 emerging， 一点都不稀奇，对吧？在高维统计里面，高维空间里面，这种聚类分类问题，对吧？这为什么叫相变理论 ？OK， 在高维统计，水从蒸汽到水，到冰，到绝对零度，就是这样的过程。Right? When you increase the epsilon, you actually reducing the temperature, and naturally corresponding to those solutions become extremely stable. Water between 0 and 100 degrees, across 2 degrees of, right, is always water. 100 degrees 变成水蒸气，对吧？每个原子全部分。而且 never only happen at 100 degrees, right? 0 degree 变成冰，对不对？它不是说-5度到了5度，对吧？先变成浆糊，对不对？模模糊糊的变成什么东西，对不对？它不是这个样子，一下子变。That's actually the reason. Why? So actually, rigorous proof this. Actually, we don't have a proof right now. But we're getting close, right? So there's a lot of phenomena. Remember, it's actually related to the phenomena you just saw in the previous lecture. Right? 那个 memorization 也是。当 sample size gets large, density gets large. So this is actually my postdoc student working on, right? So have you noticed that 像你们相变理论是除了冰和水，对不对？上有很多现象，几何的现象你们都见过。You have seen a lot of phenomena with phase transition, but they never register. You probably never realize. Right? 跟这件事挺像的，这个跟 epsilon 大小啊有关的这个事情和密度啊，你看 sample size 对吧？当 sample size grows up, when suppose the network approximate data up to certain epsilon, okay, you only have finite depths. Remember, you only do denoising up to certain steps, right? There is always accuracy. Suppose the capacity is controlled. Then remember, we increase in the number of samples. Suddenly start to generalize, 对不对？就是这些数据开始都是这么大的精度，每个点 approximate 这个精度，对吧 ？approximate up to certain epsilon. But suddenly, when the density gets high enough, suddenly everything gets connected. You start to identify that whole. You start to generalize in that entire plane. The new data you generated actually no longer focus on those isolated data points. Start to generalize, connect the entire plane, right? You only have 500 points on the plane, which is zero measure of that plane. But suddenly, majority of the data you generated, you see the entire plane. Actually, you have seen this phenomena almost on a weekly basis. 有没有同学知道 percolation 这个词儿 ？percolation 啊，你们还有很多东西要学啊，同学们，这个啥都不知道不行啊。大家看过下雨吧？对吧？躲雨的时候看看，对吧？刚刚下雨要躲在旁边下面，对吧？看你们可能就没什么看，就看看下雨嘛，对不对 ？Now just recall yourself, right? 下雨你只会见到2个 phase, you only see 2 phases. One is 开始下雨的时候 when first that drops, right? You see isolated dots on the floor, right? 这一点打湿了，那个点打湿了，对不对？稀稀落落的点，对不对？That's one status you saw. 然后呢，你会发现，啪一下，全部地方都湿了。你见过中间状态吗？ 下次下雨的时候 pay attention 啊，睁大眼睛看，好吧？你可以甚至用一个高速摄像机去拍摄，好不好？去做实验啊 ，be curious。你只会看到这两个状态 ，you only see these two phases. Why is there isolated points dots？OK，、尤其打在那个土地上啊，以前我们小时候这个操场都是那个土的，对不对？啪啪啪啪啪啪，对吧？开始打个一个凹点一个凹点，对不对？但突然一下，全部地方都湿了。You never see 哦，这里湿的多一点，那里还没粘着，对不？那里是稀稀落落的，你从来不会看到这个现象。OK，you never see that. It's always when the density of the sample 雨点啊，你看每个雨点打下来的 radius 是一样的，基本上，对不对？对，每个雨点打的就是在一个 radius。好，当它的密度啊，当它的 density reach a critical called lambda star critical density, then you can actually mathematically prove all dots get connected at that critical density. Below that, almost all dots are isolated. Okay, with the probability 1, all the dots are isolated. But once cross that entropy, once cross that density, with the probability 1, all dots get connected. Okay, 所以这个现象叫 percolation. Right? 这时候你说跟我们有什么用啊？啊 ，we use everywhere. Every single time 你拿出来这个，你在用这个现象。手机的基站就是按照这种原理来设计的。OK， 每个基站有个 fixed radius broadcasting。OK，how many base station you need to cover the city is exactly designed by this critical lambda density, so that they get a full coverage of the city. OK，it's also widely studied wireless communication. 说你们学通信的同学，如果不知道这个东西，回去自己打自己屁股啊，yes。So this is actually a lot of things. This is that a lot of things is related to the basic observations, right? 所以可以看到 this kind of spare packing. There's a lot of phenomena. So statistical phenomena, geometric phenomena, right? Related to information theory, coding theory, right? Related to quantization theory, related to partition, space partition, spare packing. Actually, in 1960s, 70s, this is a very, very popular mathematical area called metric topology, right? There's entire books about studying different space, how many sphere packing to calculate this formula for different distribution, different space, right? 不要小看这件事情。上一届的菲尔兹奖，对吧？其中一个就是给一个那个应该是波兰的还是东欧的一个数学家，对吧？一个女的。它就是解决24维还有一个8维空间中的 sphere pack 的问题。So if you can solve some of the sphere packing in certain spaces, the optimal sphere packing for certain spaces, you can win the Fields medal. Okay. Now, of course, we're not doing the hard packing, right? We're dealing with the simple geometry, right? We're dealing with subspace Gaussians. Those are already formula we already know, right? Those are we already know what's optimal packing, what's optimal formula is, right? So you can see, right? This is actually before neural network. This is IGCV 0.9, just before neural network hit place, right? You actually can use this to cluster images. Just take a token, each image patch, just merge them using different epsilon. That's it. The algorithm just does that. In order to beat all the human, actually give the state of art. This has no supervision whatsoever. Just doing dumb merging, clustering. Around every pixel, you take a window, 7 by 7 window, and you just merge using this algorithm to merge. You don't automatically decide how many cluster. Everything is automatic. There's the only parameter. This algorithm has no parameter. Okay, 0, 1 parameter. Right, compared to neural network. Right, this is fancy. Right, the algorithm only have 1 parameter, precisely 1 parameter. What is that? The epsilon. How accurate. And you can choose different epsilon. You get a different segment. From more refined segments to more gross, more 从细的分得很细的得到比较大的 right? You can see the original papers, right? So this is actually last minutes. I'll try to finish the classical story. Right. So just give you an idea, how do we measure, right? So what the heck you want to do something, okay? So what is the first? 就是叫打破砂锅问到底，这就是做科学，而且这个砂锅这个问题实际上是很 basic 的。Maybe something actually very simple, and yet everybody don't know how to answer it, right? Why do you want cluster? With what measure, right? 我不是说过吗？这个宇宙可能所有真正值得 measure 就是 space, right? The only basic quantity in the whole world is probably just space, and probably energy. But energy is equal to mass, right? Mass is just the distortion curvature of the space, unevenness of the space by general relativity. What is entropy? Entropy measures volume too. It's generalized notion of space. And what is time? Time is change of entropy. It's how space deform measure. That's it. So in the sense that if you think about it, right? I mean, even information theory, all the things reduce to something extremely, extremely basic. If you don't know what the very basic thing, right? Take whatever intermediate things, oh, this class tables, right? Or this cross entropy, or this whatever, this loss function with this least square, right? Why in the world do you do that? Right? So ask yourself sometimes, right? So now the other thing is, how about a classification then? Right? Before was clustering, right? This is no label. This is completely self-supervised, right? I just measure the volume. I want to say one. What about classification? What if I already told you this is one class, this is apple, orange, and banana. Now I have a new sample. Tell me it's apple, orange has banana, right? Tell me. Right, this is a classical classification problem. Again, right? Let's write down this mixture Gaussian, and let's parameterize with theta, but this is even for mixture Gaussian, if this is degenerate, let's do maximum likelihood, right? Find J that the theta, find the theta that is maximized, right? Turns out, again, right, if this is degenerate, this one, if this is degenerate, which means this one, the support does not go through that line, right? That is zero. Probability is almost zero for all of them. The log is negative infinity. Everybody blows up to infinity, right? Then what the heck are you computing? And nobody actually does this, right? 你们去学 machine learning 对不对？学统计、学概率，对吧？这是首先就教你们做这个，对吧？但是实际中谁用这个 classify real data？ 有人吗？对吧？20年前最 popular 的也没人用这个，对吧？做 classification 20年前最火的是什么 ？support vector machine， 对，做 nerd cutting， 对不对？对吧 ？support vector machine before neural networks，right？classification 的最火的。就是学这些 cutting class 之间学一些最优的 classification classifier，OK 现在很多没人用了但那个时候很火但后来也没人用这个，对吧？即使这个不火了，也没人用这个，最后用什么？训练 neural networks， 对不对 ？Why？ 所以这个很奇葩的事儿，对吧？我们经常教学生一些东西，我们从来都不用，对吧？完全不使用，所以这就是理论跟实践脱节 ，OK？Because the assumption for the theory looks very beautiful, looks very fancy, yeah, but it does not apply because those things are not defined when your support is negative. Support is no dimensional, right? Then you don't tell the student how to deal with that. Of course, they're going to hack. When the statistician, if the theoretician cannot tell, the method provided the condition is not fit with the real data. Of course, the computer scientist is going to hack, right? They're going to find all the kind of approximation of what is the distance between two distributions. Of course, let's do GAN. Let's approximate let's approximate Jensen-Shannon. Let's approximate the Washington distance. Let's approximate Earth moving distance because they're not defined. Then don't blame me. After I approximate several times, you don't know what we're computing. Okay? Don't ask questions, theoretician, right? Don't ask questions. It works to some extent. 所以这个是就是理论跟实践脱节，对吧？就搞自己造成的 ，OK， 是做理论这帮人自己造成的。因为我们给 practitioner 教的东西就是不实用，你的 assumption 就是不对的。对 Right? How do you do this? Right? Another idea is just very much the same, right? So if you wanted to have this to incorporate it, you want to assign a point to a new class, to a certain class. Maybe you take the minimum incremental entropy, right? Incremental volume to incorporate that to yourself. 这很简单。你在这三个 volume 里面，你看哪一个 cost the small amount of volume? Of course, if I incorporate a new sample, I'll pay some price, right? I have to incorporate that using my code book to explain that point. I may have to change my code book a little bit, right? If my code book does not incorporate that point. So I have to pay a price. I have to change, in order to incorporate, I have to change my bag size to that big. And then I have to pay a price. So the actual volume is the price I pay to have that into as one of my samples, right? 简单吧，对不对？然后 then I can measure the difference of volume. How much I have to pay in terms of volume, in terms of space to incorporate a new member, okay? Obviously, if the cost is high, I'm not willing to incorporate. You are smaller. You claim that, right? This is very simple. Again, just using the space, volume, to as a measure, very objective measure, 对吧？这也是一个不以此为转移的，对吧？这是很客观的量，就是谁花的钱少，谁用的 space 少 ，you assign to it. That's it. Very simple. So we call it minimal incremental coordinates. Whoever pay extra. Coordinate smaller, then you assign to it. Then the rest is just measure that volume. 那我们已经有 measure 嘛，对吧？这不是高斯嘛？至少 subspace case, Gaussian space, there's already perfect measure for that, right? We'll know how to compute that. We compute the difference and we say which one is better. Right. Then the volume is actually very interesting. Now, what if you let each class, the sample size goes to infinity, right? This actually works when each class has a finite samples. Right? But if I have the luxury to have each subclass has the number of sample gets higher more and more from if they're each one is a Gaussian, right? I have 5 point, 100 points, 100 points, 100 points. I can increase 1,000 points, 1,000 points, 1,000 points. I increase the number of samples. Turns out that classifier, you use just incremental the classifier actually precisely converge to a Bayesian maximum map. A posterior distribution. But also remember, this actually, if each one, the original distribution can be degenerate, this sigma can be degenerate, can be low rank. But this one, the epsilon is going to be automatically regularized, make it a generic Gaussian. 就是让它 blow up a little bit. 自动的会把一个 zero measure 的高斯把它变得肥一点变成可以 regular. So this one actually become a regular Gaussian. So the likelihood no longer blows up to infinity. So the lossy coding automatically does 让这个问题变得 well defined. 知道吗？如果你不容许 epsilon 这件事情是没有 well defined， 但加上一点点噪声 ，everything becomes。所以你可以在噪声在这里边起到另外一个作用所以这个噪声这件事情，你看上次我们在做 denoising 的起到一个作用，对不对？lossy coding 的里边 ，it actually becomes not only that， 而且你看，当这两个平面，一个是线，一条平面，对不对？如果这个离这两个距离都一样，它会往哪儿分？你想它该往哪儿分 ？Turns out this criteria always prefer this term has something to do with the dimension. It's called the geometric dimension, effective dimension of the distribution. So if two cluster, this point has equal probability to each one. This solution always prefer the one with the larger dimension. 就是你 safe 一点你胖一点我就我操胖的，对吧 ？Rich gets richer， 就是胖的虽然两边的 sample 是一样的，概率也一样，他会 prefer 这个东西，所以很有趣There's a lot of interesting behavior about this, right? So with the lossy coding start to percolate actually claim the data. So hence This is now we talk about extrapolation, generalization, 对吧? This is the only algorithm we saw. Okay, so there's a lot of classification algorithm, 对不对? 好，比如说 k-near sliver. If I have a sample like this, I use the k-near sliver. To some extent, k-near sliver is almost optimal in some sense, right? See, you get this boundary between red and blue. I'm sorry, red and green. You get this stuff reasonable, right? 好，然后呢，这是 support vector machine. 大概give you this kind of split. It's also reasonable. But this one is actually you get from minimum incremental coaching length. So it's very smooth. 而且更神奇的是什么 ？Extrapolate. You never see anything on the left-hand side, but it actually says, oh, there's maybe a line there. That line extrapolates there. So this is the only classifier we ever saw has this kind of behavior. Identify something low dimensional and extrapolates. To region has 0 samples. You have never seen anything. 所以你看很多东西很神奇，对不对 ？Neural network 没有这种 behavior。至少现在你要去专门去训练 ，OK？ 你要光是 fit 一些数据，基本上像这个 neural network 基本上 fit 像这个，很像 neural sliver 啊。可能这个光滑一点啊 ，neural 可能比这个光滑一点，更差。So this is something very interesting about, right? Identify some low dimensional, then extrapolate. Has a little bit of abstraction, extension there, right? So you can see this is something, right? Very, very interesting about the behavior of the how to measure the. Okay, the last couple of minutes, we'll wrap up here, and next time we'll talk about how this allow us to understand it's really what is the objective for us to optimize. When we try to identify the structure of the data, okay, you have to be very, very clear. What is the measure? It's not an arbitrary loss function. Oh, let's try this term. Let's try another term, right? 阿尔法数加个这个东西，加个这个 distance， 加个这个 feature 之间的这个，对吧 ？correlation 这个 sin cosine 那个，对吧？加上这个 cosine nature， 对吧？加上那个东西，对吧？我们在玩这个东西，对吧？尤其是 reinforced learning 更没天理了，对不对？对吧？现在基本上这个 reinforced learning 就把 reward function 加这 term 加个那个 term。penalize 一下 position，penalize 一下那个 speed，penalize 一下 acceleration，penalize 一下 clock，penalize center line， 对不对 ？penalize 一下 position， 对吧？加这个加那个，对吧？反正就调出来就行了，对不对？到底为什么？对吧？反正我比你好2%，对不对？I'm deserved to publish my paper, right? So it's always like that, right? So I mean, this is the point, right? If you want to really understand how do you go from the first principle? The first principle is very, very basic. So the measure you use, the loss function you use has to be basic to the point of no longer can be simplified. 明白吗？你对事情的 assumption 要少到极致，然后从那里开始能不能解释？好，那么仁爱 add a few sentence 就是这个噪声这件事情是非常神奇的一件事情。对，包括 Shannon 也是。导致他最早也是关心，对吧？就如何去 encode data, low dimensional structures, discrete samples, and so on, then continuous distributions. Then realizing there's a problem with differential entropy. Then he actually invented suggested using ray distortion, right? So to bridge the discrete and also quantized or continuous distributions, right? And that was 80 years ago, more than 80 years ago. But somehow we actually forgot those things. So how to use the noise? The noise is no longer just the roads to build from data to the world, but the reverse is also doing denoising, right? But how much we denoise, to what precision we shrink that ball close to the data matters a lot, right? The last lecture is actually showing you that epsilon matters. Using deeper epsilon, if you use a very tiny epsilon, you go to every point, it's like 水蒸气. In fact, that's a preferred solution because you want that precise, right? Hence, you might as well just memorize every data point. They don't connect. We never talk to each other because you want it to be precise. But if you allow us to have a little bit degree, at some point we start to confuse with each other. Then we start to actually connect, right? So that becomes a preferred solution. Then the points on the line get connected. Then form line, start to percolate as lines or planes. 像雨水一样，开始当密度达到一定程度的时候，在同样的 epsilon 密度增加，那么距离就连起来了，或者数量不增加 epsilon 增大，同样的，对不对？效果，那么大家就连起来。你看啊，对吧？sample 都是350个点，我把 epsilon 从小变大，开始 percolate， 对吧 ？or epsilon 的余点都是同样大，我把 density 增加，它最后也会连起来，对吧？同样的现象，我们刚才看到了训练神经网络的时候，对不对 ？sample size 从小变大，从 memorizing 到 generalization 也是这个 behavior， 对不对？甚至用 PCA 验证的都是这个，所以一定要达到这种 level 的理解。但是具体在什么样的条件会发生这件事情 ，epsilon 在哪个 level 会发生这个 phase transition，现在很多还是 open 的问题。percolation 的理论现在基本上在2维平面上是有比较好的解的 ，OK， 在高维空间中几乎还是空白，但是这些现象是一致的，这些 phase transition 都是看到了，对吧？但是在什么条件下、什么 density、epsilon 多大的时候，数据有什么分布、什么结构的时候，这些现象会发生，还没有很多定量的问题，啊，还有很多需要解决的。所以现在也是现在在研究这个 diffusion denoise 问题的一些算是 open 的问题。对吧？曲清也好，还有我的一些学生，现在都对这个问题。我们相信是有一个完全统一的理论，在高维空间中解释这种 denoising 或者增加噪声 blow up 噪声，或者过程无所谓了，你把数据增加噪声，或者是从很大的噪声 reduce 回去，到一定程度，它在不同 phase 的解会解释我们在什么条件下 prefer 不同的 solution。而且这个 measure 应该是非常客观的，就是以 volume 来刻画，以数据生成的 volume 来刻画一个统一的量，但是不同的 epsilon 不同的 regime， 它不同的解会是更加 optimal。现在这还是一个相对比较 active open 的问题啊，已经有不少的工作在做这方面的问题，至少 suggest such a unified theory is necessary is possible。very 可能今后的2-3年，可能这种东西会出来了，对吧？可能这些高维的这种，至少对于高斯 subspace， 我相信很多问题会弄得比较清楚啊。可以给大家一个解释。所以我想通过这些问题，倒不是具体的这些内容，而是考虑问题的这个思考问题啊。你今天也看到了，对不对？今天的 lecture 看到了，哪怕是做实验，对吧？做出跟人本质上不一样的事。看到真正的有趣的现象，那么还有看到现象以后的去理论解释，如何建立完整的理论的框架去解释，提供一个比较相对完整的 chain of evidence、theoretical evidence 和 experimental evidence is actually very important， 对不对？然后你对一件事情的理解可能会跟以前完全不一样啊，就不再那么稀里糊涂的，对不对？好。这个走很多弯路，说白了，我们的理论也好，理论也是，就是让你少很多弯路嘛。实际上，过去10年虽然我们取得了很大的进展，智能网络通过大量的资源啊，很多实际上是浪费掉的啊，人力资源啊，计算资源、数据资源啊，真的这些理论这样搞清楚，我们不会走很多弯路，对吧？包括干啊，包括很多东西，也不是说完全没道理，但是对吧？有更好的方法，历史上早就有的。正确的东西被忘掉了啊，被这些所谓的现在 popular 的东西，对不对非此不可的，对吧？好像觉得对吧，一定要对吧，大模型大的往下走，对不对？数据越多越好，机器越大越好，模型越大越好，对不对？真的吗？所以你们好好的回去思考一下。那么正好我多讲2句，就是因为现在你们也在你们的 course project， 好好去想一想，好吧？过去这几个 lecture 通过这些例子去想一想，去定位你们要做点什么事儿。现在机会很多，不管是理论方面，或者是现象方面，还有很多都可以值得做。而且我们把这些diffusion 的问题，应该我相信我们是解释的最清楚的了。你在全世界可能找不到这样的 document 会把这些问题解释的这么清楚。好好的弄清楚你要再学不懂我没办法了。好，那个剩下还有很多 open 的问题，是希望大家去好好去 investigate 一下静下心来认真去研究，好吧？See you next time。拜。